I'd like to welcome you to today's workshop, Discover Ansys Discovery, Teaching Through Multiphysics Simulation. So on the next slide, we'll just have a quick run through of the agenda. As I've said, I'm hosting today's workshop. My name is Harriet Parnell, but we have quite a few nice sessions, the first of which János Blocher is going to be presenting, which is an introduction to Ansys Discovery, which will last about 10 minutes. We'll then hand over to Madhumita Kumar, who's going to be doing some demonstration and presentation on our structural aspects of Discovery, before handing over to Nick Stefani, who will then be looking at some of the thermal demonstration. We'll take about a 10-minute break after Nick's presentation, just so you can just grab a breather, have a drink, walk around, whatever you want to do. And then we'll hand over to Chris, who is going to be doing fluids simulation and demonstration within Discovery. And then we'll conclude about 20 minutes after that. Actually, he might have about a bit longer than 20 to 25 minutes. And we'll have a look at some success stories and the supporting resources, particularly that can help educators with Discovery. So you can see we've got some Q&A lined up at the end of today's presentation as well, but please keep on adding your questions as we go. Okay. So on the next slide, before we start, some of these I have just run through, so I will just speed through these just not to repeat myself. Please use the chat and Q&A facility, as I've said. If you haven't already, or if you're new to Discovery, I'd like to point out, provided if you have a campus and all mechanical or CFD license bundles, but you can also put in a request for a free trial for all students. Software is free to download. I would also like to give a quick heads up for those who don't know haven't used Discovery yet, but maybe some of our other flagship models. What you will need is a discrete NVIDIA GPU for live simulation features. We may mention that a little bit as we go through, but you'll see that there's certain features within the software that the speakers will be demonstrating today where this will be required. And finally, if you like what you see today, you want a little bit extra information, we're more than happy to arrange a personalised. Do get in touch with us, education@ansys.com. And with that, I'm now going to hand over to János, who's going to lead the start of our presentations.
Yes, thank you very much, Harriet. Hello and welcome. So as part of the introduction to Ansys Discovery, I would like to first provide you with a brief overview of where Ansys Discovery sits within the product portfolio before talking about where the software comes from, meaning why it's been developed in the first place, what its capabilities are, and why it's catering well for educational purposes. As you can see on this slide, on this overview slide, Ansys offers a comprehensive software suite that spans the entire range of physics, providing access to virtually any field of engineering simulation. So we have structures, fluids, electronics, optics, and then specific packages like cloud offering, giving you access to public computing resources, or the connection section, which allows you to create digital threads and combine all these various tools. So this is just to name a few. Now, today's focus will lie on the 3D design category, specifically Ansys Discovery. Now, what is Ansys Discovery? It is a multiphysics tool that allows you to quickly explore different ideas, iterate and innovate using a range of different physics while focusing on the ease of use, which is why it's specifically interesting for students. So you can not only do fluid flow, thermal or structure analysis, but you can also couple different physics to conduct, for instance, fluid thermal or structural thermal analysis. In addition to that, it allows you to run modal analysis as well as topology optimization. Now, to better understand why we have created this tool and why it's particularly interesting for early year engineering students, I would like to start by the origins. So where does Discovery come from? Well, it comes from an industrial need, which is commonly linked to saving time and money. So here we see a typical product life cycle in which you start by defining the concept of the product, which is then taken by the design engineers to create the actual design. This is then passed on to the development stage, in which you have the engineers simulating the design to check whether they meet the requirements, before it's then passed on to testing, production, and various other operations. Now, any change or setback which forces this process to go back will be associated with additional cost and time. And the further you go within this product life cycle, the more costly and timely this change will be. Now, by speaking to customers, Ansys realized that a lot of this back and forth is actually happening between the design and the development stage. So thus we created a tool that would enable designers to perform preliminary simulation on the design to improve the decision-making process. So basically to reduce the likelihood of any pushback from the simulation engineers. So a tool for an upfront simulation was required. Now, there is some requirements associated with this. While designers, they don't generally have the same engineering background to use multiple different complex simulation software, and they also need to run through a lot of different designs fast in a robust manner. Now, this is the reason why Ansys created a tool to satisfy exactly these needs without meaning to. They also created a tool that is ideal for students because it's just very easy to use, intuitive, and can be used by non-simulation experts. Now, the software includes different functionalities into one single tool. This includes, for instance, geometry modeling, so your CAD environment, structural modal analysis, fluid and thermal simulation, but also some optimization such as parameterization, topology optimization, and scripting functionalities. Selection software from the Granter family, which gives you access to thousands of material data sheets to conduct a realistic product design case. It does all of this within a very intuitive user experience, a live physics simulation solver, which provides you almost instantaneous results, and you can still transfer all your results to our flagship software like Mechanical and Fluent to do more in-depth analysis. For you as educator, this allows you to focus really on the teaching message rather than on how to use the software or any technicalities, which is why we think this is really good for teaching early year engineering students. Now, all of these functionalities within Discovery are packaged into three main modalities in the software. So starting off on the left, we have the preparation of the geometry for simulation in the model mode. So this is your typical CAD environment with the same integrated direct modeling technology that you know from SpaceClaim, for instance. You can either prepare this within our tool Discovery, or you can import it from any other different CAD files from third-party suppliers. Now in the center, we have the Explore mode, which gives you instantaneous results where you can run a high-fidelity simulation, which runs on the CPU solvers that you're familiar with from Mechanical and Fluent, for instance. So after this short introduction, I would like now to expand on what I've mentioned previously, namely how and why Discovery is particularly useful in education. Because we see that there are two categories of students that can really benefit from using Discovery. So first of all, the non-engineering students. So we're speaking of material scientists, biological scientists, design engineers maybe, which generally benefit from including some simulation aspects in their curriculum. But oftentimes, due to the complexity of simulation software, this is not done. Now, on the other hand, you have your engineering students, so your typical mechanical engineers. They will need to learn simulation eventually, and it's already part of their curriculum in later years. And for them, Discovery can actually help bring simulation earlier in the curriculum. So let's say first and second year, and it provides a stepping stone to learning simulation generally. Now, you might be asking, what are the benefits of introducing simulation earlier? So the first one to mention here is it makes students feel like they're engineers from day one. So it's important to inspire students, convey the passion for the subject, and generally increase the engagement. Secondly, it can help in making them understand the importance of simulation and its role in many different engineering applications. And lastly, introducing such a tool really early is not, or the tool itself is not a substitute for not to substitute, but to complement the analytical teaching of theories with visualization of physical phenomena. And taking the example of an engineering curriculum, in your bachelor, you usually start with classes on fundamental topics, and then you start to consolidate those before those concepts are taken to more applied courses, into a master's, and then even into a research. Now we have the Grant to EduPack, our education-focused software for material selection and source for materials data that can support basically across the different paths through the engineering curriculum. We can see discovery being prevalent at the beginning. And then as the curriculum progresses, discovery can then be paired and integrated with mechanical and fluent. And obviously, this is just a glimpse of the Ansys product portfolio, but generally, this gives you an idea. And of course, with all that, we can support education from the first to the last day of the curriculum. So why do we think discovery is useful, particularly at the beginning? For this, we have three main aspects to look at. First one is ease of usage. You'll see in a couple minutes by our live demonstration that it's really easy and intuitive to use. If you've worked with fluent mechanical, these are just a bit more complex to navigate. Second point to mention is visualization. So students find it difficult to understand basic concepts, and visualization is a great aid, and the software can visualize basic concepts really quickly. Quick results. So setting up a model and getting results is very quick, which in turn leads to a faster learning time. And in the following demos, we would like to show you these benefits firsthand. And with this, I'll give over to Madhumita for the first structural demonstration.
Okay, thank you, Janos. Hello, everyone. I am Madhumita Kumar, and I'm part of the Ansys academic development team. Now, let us move on to the fun part, which is using the software. We will be starting with the structural capabilities of Ansys Discovery. So, Ansys Discovery has three main structural capabilities, namely static structural, topology optimization, and modal analysis. It is important to note that Discovery can only simulate linear, elastic, isotropic behavior. The contact types that are available are bonded and sliding, and only a 3D analysis is possible in this software. Now, in today's demonstration, I will be showing you two models, one focusing on the explore mode and the other one showcasing some additional features that is available with our refine mode. So looking at the two models on the slide, first we will start with modeling a beam, applying the boundary conditions. Then we will evaluate the results and evaluate the influence of material and cross-section changes. The second demonstration will be about a simple bracket under loading. Using the refine mode, we will carry out a local fidelity adjustment, and then I will show you how to transfer this to Ansys Mechanical. So let us now move on to the software. So you should be seeing Ansys Discovery now. So when you open up Discovery, the first thing that you see is our welcome screen over here. So you get a brief introduction to Discovery itself. Here you will see that it has three modes, which Janos already talked about. And you also have a small introduction to our GUI, how it works. So there are small instructive videos over here. And you also have the shortcuts for navigation, which is exactly the same as our flagship software. Same goes for the selection tools as well. We also have a very interactive help function that is available. So all you have to do is click on the F1 button. And when you point at any button on the screen, at that point, you will get an explanation about it. If you look over here, you press F1 and it immediately tells you what the different components are and how it works. So coming to the last part of this welcome screen, here we have interactive tours that are already provided and built in Discovery. So as educators, it's easy for you to teach the software to your students. You can just have them go through these different instructions, which takes you step by step and teaches you how to set up the model and run the simulation. And in case you want to learn to do, play around with the model yourself, but you don't want to create the geometry yourself, we also have sample files that are available for different type of load cases, which you can use to learn the software. Okay, so now that we finished with the welcome screen, let us create the beam in bending. So over here, this is how the interface looks like. On the left, let me point you out to three important features or areas over here. The first one is the model tree. So this one will get filled as soon as you build a model in here or you import your CAD models. This tree will keep growing. The next is the physics tree, where you will see the material of the model that you're going to be using, as well as the boundary conditions. Over here, you see structural steel, which is defined as the default, but you can feel free to change that in our settings. And the third important area during modeling is the one over here. It's called the viewing arc. This is used to change the view of the model or how the model looks like. If you want to see it in a wired form, you want to see a shadow model, whatever you like. Now, let us see how easy it is to use Discovery to build our model. Let's create the beam cross-section first. So the dimensions were 100 millimeter times 100 millimeter. So all I have to do over here in our direct modeling software is just type in the value. And it immediately adjusts the model accordingly. Now that we have the cross-section, let's extrude the model. So I use the pull tool over here. I'd like to point out that these options are almost exactly the same as what we have in our flagship software, SpaceLane. So it's nothing new for you to learn if this is something that you've already used to. Now I want a length of 1000 millimeters. And over here, you see how easily we have created a beam. So for me to escape the tool, all I have to do is press escape twice, and immediately you go out of the tool. As I mentioned earlier, now, if you can see, the model tree has now a solid inside it. So if I were to build more components into it, this tree would be also bigger. So the next part of the simulation or creating this model and setting it up is applying the boundary conditions. There are two ways of doing this in Discovery. One is the traditional way, and the next one is the cool new halo that we have available. I will be showing you both methods. So starting with the simulation tab, here we know that we want a structural simulation. So I click the drop down and then I say support. Let me apply the fixed support on this end. So you see different options over here. I know I want fixed, so I click on fixed and I select this face over here and I accept this. As soon as I did that, you can see that now there is a fixed support that has been added to our physics tree. So you know that your boundary condition has been applied. Again, to escape this tool, you click twice. Okay, so then the cool new feature that I mentioned, the halo, you can open it by clicking on the black hexagon over here. As soon as it opens up the halo. And over here, you see different options. In this case, I know that I want a structural simulation. So I click on the gear and I decide I want a force acting on the other side. So let me click on this phase. As you can see, this is not acting in the downward direction, but it's in the y-axis. So all I have to do is give -20 kilonewton. And you can see that my load has automatically changed and now it is in the downward direction. So I click escape twice. Our model is now set up. And the model is now ready to run. How do we know this? Over here, if you look at this black hexagon over here, it turned yellow. This area is called the SID, or the Simulation Information Display. When it turns yellow, it means that the model has been set up and it is ready to solve. So all I have to do right now is click on the solve button on the right. And you can see how quickly the simulation has solved. We've got almost instantaneous results. And over here to the right, you see a legend. In this case, currently we see displacement. But if I wanted to visualize von Mises stress, for example, I could do that as well. Or I wanted to look at strain in only the x direction, or the y, or the z, you can do that. So let me go back to displacement for now. Just like the viewing arc on the left over here, this arc on the right is known as the results arc. So if you want to show your students, for example, what a beam in bending looks like, you want an exaggerated displacement. So I'm going to turn these off. Another cool feature that we have in Discovery is we have monitors that are already built in, but you can also define additional monitors that you like. What do I mean by monitors? Over here, we have predefined charts over here. So in this case, for example, you can see that maximum displacement, von Mises stress, and factor of safety have been defined. So you have the values over here. Let us say now I would also like to know the mass of this beam. All I have to do is click on monitors over here and then define the value that I want, or the variable that I want, in this case mass. And I select my body, and we immediately get the value for mass. So the next part, I said we will be seeing the influence of change in material. So let us, for example, change steel to aluminum. All I have to do is double click on this. And then in the drop-down, I select an aluminum alloy. And as soon as I did that, you can see it immediately solved the problem. There was instantaneous feedback, and now we have results. And you can even validate this model this way. For example, you can see the factor of safety has decreased, which is expected when you switch from steel to an aluminum alloy. The stress remains the same. Maximum displacement has increased, and we know that aluminum had of steel, so obviously the mass has decreased. We can now also see the influence of the cross-section, but this time we will be doing it with the help of our parametrize tool, where we can parametrize certain geometries or certain load values or thickness and things like that, so we can study the influence of it on the results. So in this case, let us say that I want to study the influence of thickness. So all I have to do is click on the pull tool over here, and I use the ruler tool to see how much it currently is. And all I have to do is click on this tree button to say, okay, add as parameter. As soon as I did that, you can see that this parameter has appeared at the SID right now. So all I have to do is click in here, and I see that this is 100 millimeters. I can even change the name of this to thickness. And let me say I want to try it out for 80, and so I add 2 more design points. I say 80, 80, and 60. And I run the simulation. Sorry, sorry, this is Murphy's Law. For some reason, it didn't run. Let me retry that again. That at 60 millimeters, the factor of safety is below 0.6. And as the thickness increases, the factor of safety also increases, which makes sense. So this parameterized feature that we have, the parametric analysis feature of Discovery that we have, can be very useful in teaching students the effect or different variables have on the results or the design of the model. Now, let us move on to the second demonstration, which is that of the bracket. Since I have already shown you how the bracket, how boundary conditions work, I will just be showing you what the boundary conditions that are defined in this bracket. Over here, we have a fixed support on the left end of the bracket, and on the right, we have a 200 Newton load acting in this direction, defined by the blue arrow. So let me first start off with the explore mode. I just click on solve. You can see that the simulation has finished running over here. You see the displacement values. In this case, I'm interested in the stress values of the bracket. And over here, I can look at the values. And I notice a stress concentration zone over here. And I'm curious, what is the problem over here? Does the mesh have an influence? Because with the explore mode, you can't really visualize the mesh. What you can do is preview the size of the average mesh by clicking on this button. And when you hover it over here, you can see, for example, it's using a mesh of 0.85 millimeters. But I would like to see the mesh itself and see how it, how it's divided, how the domain is divided, and if I need a finer mesh in that area. So for doing this, we use our refine mode. So all I did was switch to the right over here, and you can see our refine mode. Now, let us say that in this region over here, I would like a mesh size of 1 millimeter. So I just define this area, and then I say 1 millimeter. Sorry, I select this area, click on local, and then say I want a mesh size of 1 millimeter in this area. And all I have to do now is click solve. So the very first thing that you notice is that the simulation takes a bit longer to run. As Janosch mentioned, the refine mode uses our flagship solver mechanical, in the case under the hood mechanical solver, which is why it's taking a little longer. And you can already visualize the mesh, and you can see the mesh is coarser in the other areas, but I would like it finer in this area, which I have been able to achieve using the local fidelity option. The simulation is still running, and now we can see that it's finished running, and now you can see the results over here. In this case, you can see exactly if the result was if the stress concentration area is caused by having too many too many elements in this area, or is it actually a cause for concern? So another cool feature that we have over here is if you want to define a better mesh, or you want to use the features that is available in mechanical after you've done an initial analysis with Discovery, all you have to do is click on this button over here, and you can see that it transfers immediately to Workbench. Okay, now let us move back to our slides. Over here. On the right, you can see a GIF of how fast the optimization simulation runs, and we obtain the optimized geometry as shown in the bottom over here. So you can see that we started off an initial geometry that looks more traditional like this, and now once our topology optimization is run, we've got a more optimized geometry over here. It is important to note that topology optimization only works in the explore mode. Coming to the next structural capability, this is modal analysis. I would like to add that modal analysis works both with our explore and refine mode. Let us look at the model setup. In this figure, we can see a tube assembly. The tube is attached to the plates using two brackets over here, and the plates are then fixed. And a remote mouse is added at the top. We can define the number of modes that we would like to visualize. In this case, it was defined as 6. So you can visualize 6 modes to the right over here. So students can get a feeling of how the vibrations look like and how the model, the modal analysis takes place, and if this is a sensible model or not. Now, let's look at a quick summary of the things that I presented today. So firstly, we used Ansys. We know that Ansys Discovery can solve 3D structural simulations. It has 3 capabilities: static structural, topology optimization, and modal analysis. We saw 2 demonstrations. One was the cantilever beam, and the second was the bracket here on the right. Important features to note are the interactive tours and help. We can quickly modify or parameterize geometry thanks to direct modeling. And using the Explore mode gives us results that can be visualized instantaneously. Thank you for listening to me today. Now I'd like to pass on the presentation to my colleague, Nick Stefani.
Hello, everyone. I'm Nick. It's a pleasure to be here and present to you Ansys Discovery. I'm just gonna share my screen. Before we jump into the software, I'm gonna share a few slides. So in the next 20 minutes or so, I would like to show you a bit of the thermal capabilities in the not only get the temperature in the solid, but also check the effect of the temperature on the structural behavior. So Mario was demonstrating structural analysis. You can also add some temperature boundary conditions there and see how temperature affect the mechanical properties, because we support some temperature dependent mechanical properties as well. We can do fluid thermal simulation, so in which we can look at the temperature and heat transfer in the fluid, and we can investigate things such as boundary layer. But also we can do the more complex of all of them. We can do solid fluid thermal simulation, otherwise known as well as conjugate heat transfer, in which we can check the temperature both in the solid and the fluid, investigate boundary layer, and also investigate the heat flux on the fluid-solid interface. Now, as part of my demonstration, I'm going to focus on the solid thermal capabilities, but later on, Christopher, in his fluid demonstration, is going to touch as well on fluid thermal and conjugate heat transfer. Now, when we speak of solid thermal, we have at our disposal different boundary conditions in Ansys Discovery. First of all, they can be accessed through the simulation tab. In the same way in which you have seen structural boundary condition, we have solid thermal panel, and these are 4 of them. You can set up a fixed temperature on a face or a body. You can set up a convective heat transfer on one or more faces. You can set up a heat generation rate on one or more faces to simulate a heat source or a heat sink, or you can set up some level of insulation as well, in which no heat will be gained or lost through a selected phase. Now, by combining one or more of these, we can set up our thermal simulations. What I would like to show you today is really along the same lines of what Mario has done, and as a common thread from this workshop, is to show 2 different examples. One, how to set up a very fundamental problem, a heat transfer in a film, which is classic problem, which is done in any very introductory class in which students have to start to deal in heat transfer, usually a first-year engineering course. And the idea is that we have this fin of